So my talk will be, I'll try to kind of go over things that, well, some of them probably were mentioned already, but for completeness, I'll try to go over kind of the main things, which we try to document in our change logs. So what you see is probably the same as the change log, but I'll add details that maybe you don't see in the change log, add some context, maybe, see if you have questions about something specific new. And so with that, let's dive in. You already saw Annie's talk and Aaron's talk. We had a release in May this year. The main thing there was we added support for single precision. So basically, we changed whatever level with RealT mostly everywhere, and the RealT is something that you can configure at build time. So you can configure either double precision or single precision. So that changes double precision everywhere. So it's the first step. That was the simplest step to take first, and that's what was done in one of the PRs. And there is some discussion about it. If you are very interested in using that, check out that discussion. There are some details of actually supported. Some of the third-party libraries. There are just a few that are supported with single precision. So this is, as I mentioned, it's the first step. Actually, I don't know. There he is there. Story. Okay, so then on the meshing side, things that are related to meshing. So this is something that I worked on. The first bullet, we added capability to partition big serial meshes. So this is, maybe not so much of theoretical interest, but definitely of practical interest. If you have meshes that you cannot fit on all processors, so kind of the standard workflow in MFEM is you load your serial mesh on all processors, do some refinement, then you partition it, and then you do more refinement. So if your mesh is so big that you cannot load it even with rank on every node, well, you have to repartition it, and this helps you do that. It's a pre-processing step. But you can also, I think, embed it in your application kind of on the fly. It will require some async, like string streams, maybe on the fly on your side. But we are planning actually to make this a bit more usable in code. And on top of this capability, I think we can build a repartitioning capability for conforming mesh. This is something that we don't currently work with. I hope it can be built on top of that. So something also kind of usage support convenience thing with this name attributes in it. So this is relatively, well, it's actually new with this in the latest release. It allows you to define attributes and give them names, just convenience thing for people who practice and move with their fan. So it's illustrated in an example of how to do that. It's not widely used in the examples because it's a new feature, so you can see it in one example right now. So there are some improvements in the NURBS refinement. You can do refinement by formula. This is, I think, by Dylan. And so NURBS are main NURBS additions. There will be a few that I'll mention. Dylan and our collaborators from Netherlands, Ido Ackerman and his group are working on that and supporting them. So I'll also mention that some capability that was added by users from basically Exodus output capability, writing various types of elements and second order elements. And I think some of these are supported, but I'm not sure we can find the pyramid and make sure we can actually use them. Well, this is something that it's coming, but right now it's capability is there, but I don't know. I'm not sure we can use it. Maybe Mark can correct me if I'm wrong. Okay, and much important can be rewritten to improve capability. So this is something that's not yet in a release, but it's already in master. So you can see that there. So there are some improvements, kind of pyramids and wedge elements, and mixed meshes. So on the discretization side, there was a big rework of example 18. The example is exactly the same in terms of functionality, but under the hood it was rewritten to make it a bit more general. So you can have a hyperbolic form integrator, which allows you to specify not just order as it was written, but other systems of conservation laws. So currently it implements vection, burner, shallow water, and Euler, which was the original thing. So you implement the flux function, you move over, it's relatively easy to add other conservation laws. So some work was related to adding integration rules on surfaces and volumes, which probably relates to embedded methods. And there is an example of that. And on top of that, I think there is a PR that's coming up soon that builds on top of this. Be more flexible in the sense of using different integration. Some theoretical mention some more. Anyway. And support for higher non-conforming element on synthesis. And this is something I'm not 100% sure why it was in the list. There must have been something that did not work quite correctly before. But anyway, now it should be fixed. Okay, and again, these are new things since the release. HDIF and H spaces, node-based spaces for HDIF conforming and H conforming elements. That I think was added in this group. And something that the aggregation class for boundary constraints, which minor improvement. Okay, GPU computing. So there will be a lot of things here. I'll not go through all of them in detail. I'll mention something that's relatively new for us is digit diffusion. So this requires the operators to be, we're talking about partial assembly here. So this is matrix free in the sense that Tani was describing this. Now, when you have DG, you have these operators that restrict things to the faces. And we've had these for advection. And we need the values of the functions at the faces. Now, DG diffusion is the next step where you need not only the values of the faces, but also the derivatives. So you have to represent the values and the normal derivative, the tangential derivative you can get from the values. So this is an addition that we will. an extension of the framework for partial assembly for DG that allows us to do that. So it allows, it's kind of some, and with this kind of approach, you can do other elasticity or anything that requires derivatives on integrating. Okay, so efficient GPU acceleration for the surfaces. This is something that's related to this version of Hyper. So since version 231, Hyper allows you to build with GPU support and then select whether you run on GPU or CPU at runtime. And before this was possible, it was running on either on the device or on the CPU, and you select that as build time. And with this version, which now is not the latest, recently Hyper team released 232, but starting with 231, you can select the runtime whether you run on CPU or GPU. So we kind of added some logic in FM to synchronize that with the choice of the FM device that you. So you say, I want FM to run on GPU, then you say, okay, you want to run off the Hyper GPU. And vice versa, if you want to run on CPU, it runs on CPU. FM, things, and Hyper. So it's configured at the beginning of the code. So full support for assembly of simplices. So this is, it sounds like a big task, but I think this is more meant to be, we have a kind of a framework how to approach that. And there is at least one example that that, and in this case, we have linear elasticity for simplices, and so this is also related to these three are kind of related. They allow you also to work on tangent product elements, quadratic hexes, and unstructured elements, which means like simplices. So there are some Raja updates here, not very important to mention, some Hyper related things. These are mostly internal for developers. If you're kind of dealing with something in the code, they were mentioned for those people like that. The main reason is really that when you have a macro and the compiler expands it, it gives you all the lines become one line, or you can't really debug well. So that's why you have to switch to a function. It's better to have a function than the line information is much more accurate. In a nutshell. So these are things that are happened after the latest release. So one nice addition was the support for partial algebra. So we have like a common class where you can dispatch, you can select, okay, I want to use QPlus, HipPlus, Magma, or a native FM functionality. And potentially you can add other packages if they are available and kind of access all of them through a single interface. Another kind of a long effort was in the area of, now if you look at the code and the build time, especially on the GPU, you will notice that some of the matrix-free kernels that are instantiated for different orders, they tend to take a lot of time. And one approach that we looked at, and this is the result of this bullet, is really a result of a PR that tries to address that to some extent, is pre-built, we want to not have the whole range of polynomials that we can support, but just have some main orders that we decide at compile time. But then if a user wants to use another, they can say add specialization and do that in their code. If it's not one of the previous. So this will speed up real time. It's the convenience thing. The code size is also going to be smaller. But there are advantages of allowing users to add specializations if they need them without putting everything, every special case in the library itself. So right now, this mechanism is added to the Fusion integrator, NAS integrator, and we can extend that to other classes in the future. That's the plan. So as you see here, the Fusion integrator as specialization is how you can tell MFEM instantiate this special case and then use it if it's actually used. That might be in a case that's not typically instantiated. And there is a way to, with an environment variable, to check if you're actually getting a case where you're an unoptimized version of the code. But as a backup, we have unoptimized versions which run for different programming orders, but they're much less performant. Okay. So now examples and mini apps. So one new mini app which was actually developed by the tribal team at Livermore is illustrating elastic contact. So this is the tribal is the library for contact. This is their GitHub page, and this is illustrated in a mini app called tribal. So this is contact library. Is Livermore, as you can see here. Yeah, so if you're interested in contact, this could be of interest to you. Let's see. So mini app to demonstrate lower the function for linear elasticity. This was added by a user. So they were interested in linear elasticity and how to do lower refined, view of applying this to GPUs using matrix-free approaches for action of the operator and preconditioning. So this was something they used ideas from what we get for problems like diffusion and other types of problems like this.
I think Victor added it.
Oh. Okay, so I'm not giving credit to feature because of course these are not things that I've done. This is, everybody has done, and a lot of them are contributions from people that are not actually in Livermore, which is it's illustration that it's we are very open, try to be very open to contributions from outside. It's something that enriches any open source project. The other two things worth mentioning. I think this example calls for something that was already mentioned before. Okay, so this is things that are new since the release. So this is the kind of was mentioned there. One mini app, plural here, so probably two mini apps to illustrate HDF and H-curve NURBS elements. There is a very nice example from Brandon illustrating this proximal Galerkin method developed by Brandon, and well, I'm not sure if that was clear or later. And the example solves the Eikonov equation with this proximal Galerkin approach. It looks very, very interesting and promising because it is a method for solving these type of problems. Well, various types of problems. I think icon equation, and what is another example that's like not compact, but compact. Sorry, compact. Okay. And then this is kind of a convenience thing for or examples. You can change the default port to the visualization center. It's giving me small wings. Report maybe one worth mentioning is the PETC integration now. It requires 321 or later, but older version may still work depending on what functionality you use. I think certain functionality had issues with older versions, so we can say, okay, we're supporting this one. Older versions, mileage may vary. Let's see. So this is again, there is a big bullet here. There was an update on how the ARC step solver, which is part of the Sundials library, also developed Livermore's, and this is related to the integration of Sundials in MFEM. This was updated, so there are some details about that. And well, it's a drafting, especially a very small thing. Custom interpolation, fine points. I think we've had very active usage and continuous updates from Keaton in the JSLib library support in FM, and very prompt response in some cases. Somebody says, oh, this doesn't work. There's a pull request the next day. So this is one of those that's mentioned here. And last bullet, there are probably a lot of things that are not mentioned here. But what I want to show, I think Sanya mentioned it. I don't believe you showed any slides on this, Sanya.
No.
So I just got to quickly mention it. So this is something that is currently in development. So it'd be interesting if you're interested in refinements that are not 2 to 1. So this is what we have currently. Right, non-conforming mesh. You can subdivide here, and this is the middle. Now with this new PR that's mentioned down here, you can select what ratio you want. So you're targeting here ratios 3 to 1, just for work with another project that uses that 3 to 1 instead of more standard 2 to 1 refinement. And so this is now, Dion is working on this NC mesh, and basically the idea is, you can define it not just in the middle, but at any point. And then if you do 2 to 1 and 2 to 1, you get 3 to 1 ratio. Illustrated here. So first you refine with 2/3 here, and then you refine this element with 1/2, and you get basically 3 to 1 ratio with 2 levels of refinement in your refinement tree. So it's kind of still using the binary, not binary, but octal tree in 3D to define this kind of 3 to 1 or arbitrary pretty much ratios.
I just want to point out that I really like the original title of this slide, which I think was 2 + 2 = 3.
You changed it.
No, I didn't change it.
I changed it. I presented it.
No, it would be. I think everybody would get it, even if you left it like. And so there is some. So this is, I guess, works for H1 right now in a branch. You can try it if you want to. This and 3D, and there is a picture here in 2D with a lot of 3 to 1 refinements, very nasty match, I guess. And it works, at least the eyeball norm. But I think it's more than that, the eyeball norm. Okay, so I mentioned another topic here that Mark is working on, pyramids. And we are almost there with support for all the spaces and arbitrary orbits. That's cool, Mark, right? Anything to add? I think the main takeout is this was not your standard elements. They don't extend that easily to pyramids, right?
Right. And unit testing is extremely important. That's awesome. It's been turning up all sorts of interesting issues we have to tackle before we can release these.
Yeah, and it pretty much this paper is mentioned here, right? On this paper. Yeah, some of the complexities are kind of mentioned here, rational polynomials from variables. But this is from Exxon as well. And this is illustration for HD spaces. Some picture that I didn't quite understand if I look at it a little bit. Maybe somehow we point this way, but then the other half points the other way. Kind of interesting. I'm not sure how it works, but other HD bases on pyramids are probably not easy to visualize and in your head at least. The geovis should be once you have the basics. Okay, and the last thing I want to mention here is again something that's working a branch. It's not after yet. It's not in release, but this is work by Jan, and he will talk about it in more detail. I just want to talk about its convection diffusion with some anisotropies, and there are some results here, but I'm not going to steal. These are just some slides with pictures. Otherwise, I was showing mostly slides without pictures. Okay, so going through GeoVis, I think most of these were already mentioned in some, in what Sonia talked about. The main thing for the new GeoVis release, as mentioned here, the next one of the bug fix, things that were fixed a month later, was the visualization of quadrature data. That's also something Jan worked on, and he is the main author. These are the three options that Sonia mentioned for visualizing that data. Okay, it mentions here that you can switch between these three options with the Shift Q. So there was a lot of discussion on this topic actually, auto refinement. So we decided that before the way GeoVis work is you give it a mesh and it will look at how many surface elements it's drawing, and it will auto refine. If the mesh is coarse, you'll get very nice and smooth looking surfaces. But as you start drawing more and more refined meshes, you may see that like your curvature disappears. And that's because GeoVis decides that, well, this is a fine mesh, so to speed things up, you're not going to sub-refine it. You see it like a linear mesh and you wonder, well, what's happening? Where is my curvature? And the reason it's just visualization. We were doing it for speed, and that number was fixed for quite some years, but now with new hardware, we said, okay, it's probably not worth keeping it low. So now we allow, I don't know, one of the orders more refinements. So this may lead to maybe, if you're loading a big mesh, it gets refined, so your window may pop up late by a second instead of instantaneously. That's something. The discussion. I wanted to put up a phone to you. Other people, you want to see the real function. If we have to wait 1 second. And Yeah, this is an addition kind of also for how we visualize floating point numbers. Something that you have to highlight as well. I think that was the question from the user and please, it's very simple. So this is also something young with it, integral finite elements, they were not really tested and supported well in the evidence, so we run through the code and make sure that now integral finite elements are visualized correctly and you yeah, also added some new modes for visualizing 2D fields. We already have maybe 3 or 4 modes. This is adding 2 more, just depending on the field you have and how you want to view it. It's a different option. And I think mentioned that in programming, it's major thing for functionality, but these things, it just means you can visualize bigger images. So these were already mentioned. I have them here. The MFEM at LLNL seminar tutorial and actually highlighting MFEM. I don't have slides for things in MFEM. Unfortunately, I didn't have the time to compile a set of changes. Anyone has knowledge? Maybe they can mention quickly something new that's worth mentioning about MFEM.
I think the main thing was catching up to support the latest version of MFEM, importing additional examples, the Python version, and some CI improvements and testing improvements. Is that correct, Justin?
Yeah, I think we wanted to have a CI connector basically when we update MFEM to automatically that would be tested with the MFEM CI. I think now this is possible automatically. Okay, and that's
Let's thank Vesselin.